So now moving on to weak bases. They are basically the same thing, but they, instead of donating a hydrogen ion, they accept hydrogen ions. And they do it to a small degree, right? Weak bases accept fully 100%, and they create 100% hydroxide. Here, we're going to accept a small amount of hydrogen ions from water, and then we're going to be left with a little bit of hydroxide. And so we also have equilibrium constants for these bases. They are called Kb, and the larger the Kb, the stronger the base, just like with acids. So we're going to do the exact same calculations. The only difference is now that we have bases, we're going to have a generic base reacting with water to produce. Now it's going to take a proton from water, so it's going to become the conjugate acid, and we're left with hydroxide. So instead of forming hydronium, we form hydroxide. So that should be a good indicator that we're going to get something like POH over here instead of pH. Bases can either be neutral molecules that can accept a hydrogen because they have a non-bonding pair of electrons. Many of those are ammonia and amines. So nitrogen is a great element to do that because it has a lone pair of electrons and is not super electronegative like oxygen. So it's willing to share its lone pair with a hydrogen atom or hydrogen ion. We also have our anions of our weak acids, which are conjugate bases. So for example, remember if I have a weak acid like HF, its conjugate base, fluoride, is a weak base. So weak acids make weak bases make weak acids. And so this weak acid here made fluoride. Fluoride is a weak base. So if I have sodium fluoride, the salt, here's fluoride's an anion. Fluoride can interact with water to produce hydrofluoric acid and hydroxide. This hydroxide part here indicating that fluoride is a weak base. So let's practice. Here are some examples of weak bases. Notice a lot of them have nitrogens on them with lone pairs of electrons, and some of them are conjugate bases of weak acid. So carbonate, conjugate base of weak acid. Hydrosulfide ion came from hydrosulfuric acid. Hypochlorite ion came from hypochlorous acid. And so they all have Kb values. And actually, you can see here are weak acids, and so here's hydrofluoric acid like we had talked about earlier. Hydrofluoric acid, it has a Ka value, and we can see fluoride is its conjugate base. It has a Kb value, and these two are related by this equation. Ka times Kb for an acid-base pair, okay, so for example, hydrofluoric acid and fluoride, equals Kw, which at 25 degrees Celsius is, Kw is 1.0 times 10 to the negative 14. So if you know if I know hydrofluoric acid's Ka value, then and I have fluoride in water, then I could solve for the Kb knowing the hydrofluoric acid's Ka. So let's calculate the Kb for the fluoride ion, knowing that Ka, for HF is 6.8 times 10 to the negative 4. And we're going to solve for the Ka of ammonium's ion, knowing that the Kb of ammonia, NH3, is 1.8 times 10 to the negative 5. Okay, so fluoride is a base, so I'm going to actually just show the dissociation in water to produce hydrofluoric acid and hydroxide. You don't have to do this, but that's fine. So if I want to know the Kb of fluoride, I'm going to do Kb times Ka equals Kw, which is 1 times 10 to the negative 14. So now I can do Ka or Kb equals Kw over Ka So I'm going to get 1.0 times 10 to the negative 14 divided by 6.8 times 10 to the negative 4. And I get 1.5 times 10 to the negative 11, which we saw on the last slide. So that's correct. Now for ammonium. Ammonium is NH4 plus. When that's in water, it's going to produce hydronium and ammonia. Okay, so ammonia's Kb is 1.8 times 10 to the negative 5. So I could do Ka times Kb equals Kw. I'm going to solve for Ka. So I'm going to divide both sides by Kb. So Ka of ammonium equals Kw, 1 times 10 to the negative 14, divided by the Kb of ammonia, 1.8 times 10 to the negative 5. So I get this value to be 5.56 times 10 to the negative 10. That's the Ka for ammonium, NH4 plus. Here I have quinoline's conjugate acid. It has a pKa of 4.9 times 10, which is 4.90. So what's the base dissociation constant? So a couple ways you could do this. You could find Ka for quinoline by doing 10 to the negative pKa. So you'll do 10 to the negative 4.90 and then plug it on into this guy here, just like we did over there. Or you could do the fact that if I took the negative log of this expression right here, I get pKa plus pKb equals 14. So I could do pKb for quinoline's conjugate base is 14 minus 4.9, which is 9.10. And then I could do the Kb equals 10 to the negative 9.1, which equals 7.9 times 10 to the negative 10. Okay, now let's start to do some ice tables. So what's the pH of ammonia of a 0.15 molar ammonia solution? So we have the dissociation. I've drawn it a couple times now. Let's do the expression. Kb equals products over reactants. So ammonium, NH4 plus, times hydroxide over ammonia, NH3, brackets, okay. We saw earlier that the Kb for ammonia is 1.8 times 10 to the negative 5. Okay, so let's do our ice table. Here I have 0.15 molar of ammonia. Sorry, it's easy to switch those up, they're so close. So I'm going to lose x, I'm going to gain x. So I have 0.15 minus x, and then x. Now we still get to do the approximation, so I can take my initial concentration divided by Kb, see if I'm close to 1,000 or higher. So if I do 0.15 divided by Kb, 1.8 times 10 to the negative 5, just finding that factor, positive, a whole number factor. I get about 8,300, so much more than 1,000. So I am good to make the approximation, which would mean that I have x squared over 0.15. I do not need to do the minus x, so that's great. So multiply both sides by 0.15, and then square root to get x by itself, and you end up getting so x, which now x here is hydroxide concentration, is 1.64 times 10 to the negative third. So now if I take the negative log of that, I get POH. So that's like one of the biggest differences here is I have to do an additional step to get pH. So POH is 2.78. And so I'm going to do 14 minus POH to get pH. which equals 11.22 is my pH. So has a higher pH above 7. That's a good indication that I have a base. There was another problem in between there that just had a smaller concentration of ammonia. So in that one, you will have to do the whole quadratic. I'm going to skip that because I feel like you've done a lot of that practice. So carrying on, we're going to create a solution adding sodium hypochlorite in enough water to make a 2-liter solution that has a pH of 10.5. So calculate the number of moles of sodium hypochlorite that you need to add to the water. So already you might be like, whoa, too much. Moles? I thought it was a molarity. That is accurate. You're good. Just keep in mind, we're just doing the same thing we've been doing. Key thing here, if you see any group 1 ions, sodium, potassium, lithium, you're going to just ignore them. They always completely dissociate. They're very soluble. We'll learn about later. And they are, so they're just going to be spectators. So what we really have here is hypochlorite in water, and it's going to make hypochlorous acid and hydroxide. So it's acting like a weak base. Now, hypochlorous acid has a pH of 3 times 10 to the negative 8. So the Ka for HOCl is 3.0 times 10 to the negative 8. So from the stuff we did earlier, I can find the Kb of OCl, of hypochlorite. So to find that, I'm going to do Kw equals Ka times Kb. Now we know the Ka goes right there. So I'm going to do 1 times 10 to the negative 14 divided by the Ka equals Kb of hypochlorite. So let's do that. 1 times 10 to the negative 14 divided by 3 times 10 to the negative 8. And I get my Kb for hypochlorite is 3.33 times 10 to the negative 7. Okay, so we have recognized that we have a base. It's in water. It's dissociating. We calculated its amount, and you could have also looked at the table. I'm just doing it the old-fashioned way, with if you didn't have the Kb, but I did give you the Kb in one of the tables above, so you could have skipped that whole step. That's fine. It's good practice though, right? Before I do my ice table, I want to write my Kb expression. Since we just had our Kb, we solved for it, let's do our expression, which Kb equals products over reactants. So our conjugate acid times hydroxide over the base. Okay, great. So here, I'm now going to set up my ice table. And we are going to find out how much, so I'm making a solution. It has a pH of 10.5. So, and I want to find out how much sodium hypochlorite I need to add. So I want to find out basically how much I need to add here. Knowing that I don't have any any products to start off with. Okay, so now the key piece of information we have here is that the pH is 10.5. So that means that my pOH is 14 minus 10.5, which is 3.50. So then I can find out my hydroxide concentration by doing 10 to the negative pOH. So my hydroxide concentration is 10 to the negative 3.5. So I end up getting a hydroxide concentration that is 3.2 times 10 to the negative 4 molar. And that's what I put here for my equilibrium hydroxide concentration. So that's how much I am going to have in my change column. So let's put that up there. So that's how much I'm changing, and that's how much I'm going to actually be changing for my other product. Gain that much. And then I'm also going to lose that much from my reactant. So putting that right here. Okay, so then at the end for hypochlorite, I have the much amount I started with in concentration minus 3.2 times 10 to the negative 4. So I have my equilibrium amounts. Here I have, they're all filled in, only one unknown. So I can plug that in now. So let's plug that into KB. So KB, which is 3.33 times 10 to the negative 7, which we solved down here or looked in the table, equals my products, which are both 3.2 times 10 to the negative 4. So I'm going to square them, divided by x minus 3.2 times 10 to the negative 4. So what I end up getting, when I solve it all out, I'm going to cross multiply here. So the denominator, or my one side's going to come down to the denominator, and my denominator is going to come up. So I'm multiplying up and then dividing down. So I get now x minus 3.2 times 10 to the negative 4 equals 3.2 times 10 to the negative 4 squared over 3.33 times 10 to the negative 7. And then I can now add 3.2 times 10 to the negative 4 to both sides. So after we do that, this crosses out, we get x equals, so we will just do that math. Literally just 3.2 times 10 to the negative 4 squared times, or divided by 3.33 times 10 to the negative 7 plus 3.2 times 10 to the negative 4, and you get 0.308. So x, the initial amount of hypochlorite you have is 0.308, and that's in molar. Remember, we're dealing with KCs here. Even though I know we're writing Ka and Kb, they came from Kc, right? Concentration equilibrium. So we should not be in these tables when we are using a Kb here. We should be using concentrations. So don't go into moles. Now that we have the moles, we know that this is in technically moles per liter, and we made a 2-liter solution. So if I multiply by 2, then the number of moles of sodium hypochlorite I needed to add is going to be 0.616 moles. Okay, let's do another one. In these ones that we're kind of doing, we've gotten the hang with the acids of, finding Ka, finding pH. Now in this one, we're actually finding the concentration of an ammonia solution where the pH is known, and we know the Kb. So here's our reaction. Our Kb is products over reactants. So ammonium times hydroxide over ammonia. Okay, the Kb is 1.8 times 10 to the negative 5 for ammonia. So here I have my ice table. I know that I am starting with 0 products, and I want to find the concentration of ammonia. So I want to know what X is. That's what I'm finding is my initial concentration of ammonia. So now I know the pH is 11.17. So then I can find the POH, which is 14 minus that. So I end up getting 2.83. So then my hydroxide concentration is 10 to the negative 2.83, which is 1.48 times 10 to the negative 3 molar. So now that's going to go in my hydroxide equilibrium. So then I do know that that is the change for hydroxide. That's how much I had to increase hydroxide. So since I know the change there, I also know that's what my other product had to gain. And then I know that is how much my reactant had to lose. So minus. So at equilibrium for ammonia, I have X, how much I started with, minus 1.48 times 10 to the negative 3. So what I'm going to do is go put that into my Kb expression. So I have 1.48 times 10 to the negative 3 squared over X minus 1.48 times 10 to the negative 3rd. So once again, just like we did before, I can cross multiply. So bring my numerator down, bring my denominator up. So I get X minus 1.48 times 10 to the negative 3rd equals products 1.48 times 10 to the negative 3rd squared over my Kb, 1.8 times 10 to the negative 5. Then I'm going to add 1.48 over to both sides. So then I get X, which is my initial ammonia concentration. So let's do that. 1.48 times 10 to the negative 3rd squared divided by Kb, 1.8 times 10 to the negative 5 plus 1.48 times 10 to the negative 3rd. Oh, math, so fun. So my initial ammonia concentration is 0.123 molar. Great. Okay, that is how you do those problems. So remember I told you you can either know your initial amounts, at least one equilibrium amount, or your K value. So we've done a lot where we've done those two, initial and equilibrium, or where you've done equilibrium or initial and K, and then you are able to find equilibrium amount, right, like pH. But now we just did where you know K and equilibrium, and you had to find initial. So there's always going to be one unknown, so you're just solving for the thing you don't know, by all the things you do. So now we're moving on to the next section, which is when we have salts and how they interact with water. So when we have an ion react with water to create hydronium and hydroxide, this is called hydrolysis, or breaking up of water. And so if I have a salt, right, an ionic compound, so let's say M plus, or MX, where M is my cation and X is my anion, I want to determine if this whole salt, if I put it in water, is going to produce an acidic solution or a basic solution. I want to look at the cation and anion separately. So the cation here could either be acidic or neutral, and the anion can either be basic or neutral. So let's talk about how that works. So if I have an anion that came from basically think of every anion as a conjugate base of an acid. So I could have my anion with water to produce my conjugate acid, so the weak acid, plus OH. So in this case, no matter what, I could theoretically have an anion create hydroxide. When my anion came from a strong acid, though, remember, strong acids make negligible bases. So if I have Cl here with water, theoretically I'd make HCl and hydroxide. But hydrochloric acid is so strong that it pushes the reaction backward, and I will never actually form HCl. So hydroxide will never get formed. So if I have an anion that came from a strong acid, they are always going to form a neutral solution. So as a reminder, the strong acids are HCl, so chloride would be a neutral base. HBr, so bromide would be. HI, so iodide would be. We also have chlorate from chloric acid and perchlorate. and then nitrate, and also bisulfate. So if you see any of these guys in water, you know they're neutral. Everything else is going to be basic. So anions that came from weak acids, so here's acetate, they're going to form weak acids. So we're going to form acetic acid and hydroxide, and there will be a significant amount because since acetic acid has a Ka, that means acetate has a Kb, so it does act like a base. So that's the gist. If it came from a strong acid, neutral. If it came from a weak acid, they're basic. For cations, so these are the metals out front, or just the general positively charged portion of the salt out front. If we see something that came from group 1 or group 2, this is alkali and alkaline earth metals, they are neutral. If you see anything else, it is acidic. So that anything else could be a polyatomic cation that came from weak base, just like we had above. So here's ammonium, came from ammonia, right? So that gets formed. Or we could also have group D and F metals. So even though they don't have any protons to donate, why are they acidic? Let's learn. So what they do, these transition and post-transition, so again, group D and F metals, they form hydrated compounds or hydrated ions. So what happens when they dissolve in water is that waters come and attach to them. And they come attach, and if that attachment is big enough, then they dissolve. Cool, we've talked about that with solubility. But by this hydrating, these waters are attached. The oxygen, which is attracted to the positive cation, is being pulled. The electrons are being pulled, which indirectly causes a side water and a separate water that's not hydrated to be able to pull on this more weakly held hydrogen that's attached to that hydrated water and pull it off. So the stronger this pull from the cation, the weaker that the hydrogen on the hydrated water is held, so the easier it is for it to come off, so the stronger the acid. So we end up getting this hydronium off. So again, we have these water molecules that come around, hydrate the ion, the cation. They are being pulled into the oxygens are being pulled, the electrons are. So they weaken the hold on this hydrogen atom connected to the water. So surrounding waters are able to come in and pull off the hydrogen to create hydronium. So you can see here that I'm creating the water that is attached to the metal is more acidic than it would if it was just neutral, free waters. So we get this acidic solution. The stronger the charge, so here's these +3s, they have all higher Ka values than these transition metals that are +2. So higher charge equals more acidic. Okay, so in general, if I have a group 1 or 2 metal, we know that is neutral. And if it came from an anion of a strong acid, that is also neutral. So I'll have a neutral solution. If I have a group 1 or 2 metal cation, again, neutral, with an anion of a weak acid, that's basic. Remember, weak acids make weak bases. So this will be a basic solution. I have not a group 1 or 2 cation, so that is acidic, with an anion from a strong acid, that would be neutral, so I'll have an acidic solution. And if I have a non-group 1 or 2 cation so that would be acidic, with an anion of a weak acid, so that would be basic. Then basically we have to compare the Ka of the cation to the Kb of the anion, and whichever is greater will tell you what the salt is. So if Ka is greater than the Kb of the base, then it will be acidic. If Kb is greater than the Ka, then it will be basic. Okay, now let's look. Now you're gonna need your periodic table because you're gonna need to look and see where these different metals are. So barium, that is a group 2 metal. So this is neutral. Remember, it's unless if it's group 1 or 2, it's always neutral. Now this is acetate. So you have to ask yourself, is acetic acid a strong or a weak acid? Well, it's not a strong, so it's a weak acid. So this will be a weak base. Weak acids make weak bases. So this overall have a neutral plus basic. So this is overall going to make a basic solution. Okay, now the cation here is ammonium. That is not group 1 or 2, so this is acidic. Then I look at chloride. Did it come from a strong acid? Well, Cl's acid is HCl. That is a strong acid, so this will be a negligible base or neutral. So this salt will be acidic. Okay. Now this looks pretty big, but keep in mind that this is an amine group that has been protonated. So it's not group 1 or 2. That's the main point here. Not group 1 or 2. So it's acidic. And bromide, did it come from a strong acid? Yes. HBr is a strong acid, so Br is negligible base. So this will be an acidic solution. Okay, potassium, group 1, so it's neutral. Nitrate, did it come from a strong acid? HNO3, nitric acid, yes, it's strong, so this is neutral. So potassium nitrate, neutral. Now aluminum, is it group 1 or 2? No, it's a transition metal. It's over in the P block actually. So this will be acidic. And then we have perchlorate. Does it come from a strong acid? Yes, perchloric acid is strong, so this would be neutral. So then this is overall an acidic solution. Great, that's basically the gist. Okay, if I have a polyprotic acid, that means these are the acids that have more than one acidic proton. So more than one proton that's weakly held. And in general, it's always easier to remove the first proton than the next one. So they're going to have different Ka values. So here we see ascorbic acid, 10 to the negative 5 for the first one, decent. 10 to the negative 12 for the second one, so pretty weak. And in general, if the Ka values for each dissociation have a difference of like 1,000 or greater, then the pH really only depends on the first dissociation. So we can see here there's a factor of like 10 to the 7. So basically this first one's going to be important. Here we have 10 to the negative 7 and 10 to the negative 11. So that's by a factor of 10 to the 4. So that's going to be only dependent on the first one. Here I have 10 to the negative 4 and 10 to the negative 5. So for citric acid, we actually do have to care about both. And then even the third one's pretty decently sized, only about 100 times different from the second one. Oxalic acid has about a factor of 1,000, so that's pretty close. Phosphoric acid, the first one's a lot stronger than the second one and the third one. Sulfurous acid, quite strong for the first one and weak for the second one. And then tartaric acid, off by about a factor of 100. So we look at these values, off by a factor of 10 to the 2. So we would have to care about that. So again, first one comes off easiest, and if they're off by a factor of 1,000, just treat them as a monoprotic acid, just a regular old weak acid. If they're less than 1,000, then we need to look at both of them. So let's see how that works out. So here it says solubility of carbon dioxide in water with a 0.1 molar is 0.0037 molar. Now this is from Henry's law, so this is sidebar. Common practice is to assume that all dissolved CO2 is form of carbonic acid, which is produced in this reaction. So we have carbonic acid, that's a weak acid. So what is a pH of a 0.0037 molar of carbonic acid? So here, let's first draw the first. So we have carbonic acid in water. Let's write the first dissociation. So that would be hydronium plus bicarbonate. Okay, and this has a Ka. That is carbonic acid. The first one from that table is 4.3 times 10 to the negative 7. Great. Okay, now the second association I'm going to write down here, 8. So I'm going to take this proton off now. So bicarbonate plus water is going to produce carbonate. Oops, I'm actually going to do the same order as before. So hydronium, doesn't matter technically, plus carbonate. And that has a Ka value that is, from the table, 5.6 times 10 to the negative 11. So if I take those two numbers and divide them by each other, then I'm going to see that I have a difference of about 7,700, so 7,700. So this tells me that I don't have to worry about the second reaction down here, the second association, when I calculate my pH. So let's do that now. I have 0.0037 for my initial concentration, and then 0 to begin with. Let's also write the Ka expression, which is hydronium times bicarbonate, divided by the acid, carbonic acid. So then I'm going to do plus x minus x, 0.0037 minus x. Okay, so let's make sure, can I make the approximation? Probably. Let's see. So it looks like my initial concentration is about 8,000 times higher than my Ka. So I'm going to do the approximation. And my Ka is 4.3 times 10 to the negative 7 equals x squared over 0.0037. I'm going to multiply. And then square root. So we end up getting our hydronium concentration, I guess I'll write it down here, is 3.99 times 10 to the negative 5th. So my pH is going to be negative log of that. And so that will give me a pH of 4.40. Okay, so carbonated water is pretty acidic, which is why if you've ever drank it, it kind of has a little bit of a sour taste to it. Okay, so now we're going to do this one with ascorbic acid. So we want to find the pH of a 0.1 molar ascorbic acid solution. So I'm just going to call it H2A because there's two of them in water. So let's write the first association of hydronium plus my conjugate. Well, I keep doing that. And conjugate acid. Okay, so then my Ka for that is going to be hydronium times Ha minus over H2A. So there's my ascorbic acid. Okay, that has a value of 8.0 times 10 to the negative 5, and we can see that on that one chart. Okay, great. Let's also write the second association while we're at it, Ha minus, so that's ascorbic acid that's been deprotonated once. Let's deprotonate it twice. Get hydronium plus A2 minus. So Ka2, let's label this one up there, 1, equals hydronium times A2 minus over Ha minus, and that equals 1.6 times 10 to the negative 12. So when I'm trying to find my pH, these numbers are so far away that I just have to look at this first one, the first Ka expression. But for part B, I want to find that completely deprotonated ascorbate. So we're just going to go all the way. So I have initially 0.1 molar of ascorbic acid, no products. So I'm going to go minus X plus X. So 0.1 minus X. Now we know that Ka is pretty small, 10 to the negative 5 compared to that initial amount. So I'm going to make the approximation. So I have 8.0 times 10 to the negative 5 equals X squared over 0.1. So we're going to multiply it by 0.1 molar and then square root. So X, which is hydronium, in this case, is 2.8 times 10 to the negative third molar. Okay, cool. So we know that to find the pH, I could just stop here. So negative log of that is going to be equal to the pH. So negative log of 2.8 times 10 to the negative third is 2.55. So we could be done here. To find the ascorbate concentration, what we're going to need to do is bring down what we know. We know that, let's actually write it in blue, X is 2.8 times 10 to the negative third. So I can write that in here now. And then I can put that, that's now, I initially am going to start with that much of my biascorbate. So 2.8 times 10 to the negative third. And that is also how much hydronium I have to begin with. So 2.8 times 10 to the negative third. And I don't have any of the ascorbate in there yet. So now I'm going to, again, lose some X and gain some X from my products because I don't have any of my ascorbate. So I have 2.8 minus X, times 10 to the negative third minus X. And 2.8 times 10 to the negative third plus X and X. Okay, so now we're going to plug into Ka2. So we saw up there Ka2 is 1.6 times 10 to the negative 12. Now this is so tiny. So now what we get to do, which we'll learn next chapter more explicitly, is we get to now get rid of the plus and minus X's right here when we plug in. So I'm going to do hydronium, which is 2.8 times 10 to the negative third. And I don't need to do plus X because I'm going to gain so much less, right, that we'd said it would be insignificant for the pH, that plus X isn't going to matter. Then I'm going to multiply by X, and then divide by 2.8 times 10 to the negative third. Minus X, but we're not going to worry about the minus X. So now you can see that the numerator and denominator cancel out because they are the same. And so our X here, which is our ascorbate concentration, is 1.6 times 10 to the negative 12 molar. So pretty small. We don't make very much of it. Okay, last thing we're going to talk about in this chapter is our last definition of an acid and a base. So remember Arrhenius made the first one that was acids have hydrogen ions and bases have hydroxide ions, and that was okay, but wasn't very inclusive. So then Bronsted-Lowry came up with the definition that an acid is a proton donor and a base is a proton acceptor, and that made more inclusive for our weak acids and bases basically. But that still doesn't explain some things like our metal cations. So like, why are those considered acids? So we need something a little bit more inclusive, even more. So now instead of dealing with protons and proton donors and acceptors, we're going to think about electrons. So Lewis acids before, and you know what's kind of cool about this is Lewis definition still works with Bronsted-Lowry. Before, if I had my little hydronium over here, if it was going to be donated, let's say onto a water, for example, or even ammonia, it's going in here and it's going to need an electron, a lone pair. So now the definition is Lewis acids are electron pair acceptors. So they need some electrons, right? They're electron deficient. And then Lewis bases are electron pair donors. They have the electrons that the acids need. And so they are electron rich. They have a lot of electrons. In organic chemistry, you'll talk about these Lewis acids, or electrophiles are very common, right? Electron loving, so they're needing electrons, and nucleophiles for bases because they're kind of attracted to the nucleus, which is a positive charge. And keep in mind for bases, when we have a higher electronegativity, they're not as good of bases because they don't want to share those electrons. So keep that in mind when we look at our bases that have lone pairs. So oxygen, mediocre. Fluoride, not very good. But something like nitrogen, better because it's less electronegative, so it's able to share those electrons. Okay, so like I said, all Bronsted-Lowry acids and bases still meet the Lewis criteria. But there are some that don't qualify as Bronsted-Lowry, but they do meet Lewis. So here is ammonia with hydronium to make ammonium, right? Deficient in electrons, rich in electrons. There's that base and acid. So that's good for Bronsted-Lowry. But now we have something like boron trifluoride here, which is electron deficient, right? It doesn't have that complete octet. And so we can have our lone pairs from our base go in here to this electron deficient atom and create that extra bond. This is called an adduct. And then it also helps to include our hydrated metal cations, right? Because they are bonding with the electron pairs from water, which by like indirectly causing the surrounding waters to take more hydronium from, or hydrogen ion from those hydrated waters. And keep in mind that that higher charge of those cations make a stronger bond to the water, so we get a weaker attachment to their hydrogens in those hydrated waters, making them stronger acids. Okay, so this finishes this chapter, but next chapter we're just gonna keep on keeping on with the same concepts, so don't forget anything.